Hello and welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we will learn how to conduct a test of hypothesis for a parameter in our population. So as we discussed in chapter 7, there are two methods which we can use to make inferences about a population parameter. The first method is to estimate the value using confidence intervals. And then the other method is where we can make a decision about a specific value of the population parameter. So basically, we will conduct a test of hypothesis about these values, and that's what we will learn in this lecture. So let's start with an example and see what type of problems we can solve here. So consider that a manufacturer that purchases electric light fuses in lots of 10,000. And suppose that the supplier of the fuses guarantees that no more than 1% of the fuses in any given lot are defective. Okay, so if you think about it, the manufacturer, he cannot test each of the 10,000 fuses in the lot, but he has to decide whether to accept or reject the lot based on the examination of a few fuses or a sample of fuses. Okay, so let's say he picks a sample of size 100, assuming it's a simple random sample and it represents the population. And let Y be the number of defective fuses. So now, if the number of fuses is large or it exceeds 0.01, which was the claim, if it exceeds that, then we have a larger number of defective fuses than was claimed. In that case, he would have to decide whether he wants to keep the lot or send it back. So if it's more, he would send it back. If not, he will keep it. Another scenario, suppose an investigator for the EPA wants to determine whether the mean level mu of a certain type of pollutant released into the atmosphere by a chemical company meets the EPA guidelines. If 3 parts per million is the upper limit allowed by the EPA, the investigator would want to use, again, a sample data to figure out if the company is violating the law or not. And the company would be violating the law if the mean value is greater than 30. So mu greater than 30 is what we are trying to test. Okay, so in this EPA example, what we can do is we can conduct a test or we can conduct a test of hypothesis to test to see if mu is greater than 3. And the way we will do this, the method, we will discuss the method here, is a method similar to the proof by contradiction. So basically we will call the value that we are trying to prove, mu greater than 30, we will call it the alternative or the research hypothesis. Here is how it works. So the alternative hypothesis will be denoted by HA, and the contradictory theory would be that mu is equal to 3, which is our null hypothesis, and it is denoted by the symbol H0. Okay, so the EPA is trying to prove that the alternative hypothesis mu greater than 3 by obtaining samples from the population. And if it doesn't have proof, then the null hypothesis will be true. That means mu is equal to 3. So for conducting a hypothesis test, the first step is to state the null and alternative hypothesis. So depending on what your parameter is, in this case, the parameter is mu. So H0 mu is equal to 3 and HA mu is greater than 3. So the rule that we follow is H0 is always with the equal sign. That's the value that we are comparing our sample value with. And HA is the alternative hypothesis. It can be with a greater than sign, less than sign, or a not equal sign. So now the next step is to basically make a decision whether we want to reject the null hypothesis or we want to fail to reject the null hypothesis. And this will be based on a statistic which is called the test statistic imputed from the sample data. So once we have the null and alternative hypothesis stated, the next step is to gather information, pick a sample, gather information from that sample, and then calculate this test statistic. Now, the test statistic formula will vary with our parameters. So once we discuss each parameter, we will have a specific test statistic formula associated with it. Now, in this example, let's say the EPA plans to base its decision on a sample of size 30. We have 30 pollution readings. If the sample mean of these 30 readings is much larger than 3, then the EPA would reject the null hypothesis and conclude that the mean is actually greater than 3. Okay. However, if the sample reading is less than 3, let's say the sample mean is 2.8 parts per million, then we do not have sufficient evidence to refute the null hypothesis. And in that case, the value mu equals 3 will be accepted. So here is how we can decide what value is large enough. So we have 3 in the center, but we want to figure out how large is large. Is 5 large? Is 6 large? Is 6.5 large? So for doing that, what we do is we use the distribution of our sample statistics. So let's say for mean, the point estimate is x bar, just like confidence interval. And then if we use the distribution of this x bar, which is normally distributed, we can basically divide that distribution into 2 parts, or we can have 2 sets of values, whereas one set of values will be, let's say it's a greater than test. So if our sample statistic falls in that greater range, let's say more than 5 is where our rejection region is. That region is called the rejection region. So if our sample value falls in that larger area, then we will reject the null hypothesis. If we have this value within the lower part of the 2 parts or the 2 regions, then we will fail to reject the null hypothesis. Okay, so let's look at this example again. So we're trying to test 80 mu equals 3 versus the alternative hypothesis mu greater than 3 by using a sample mean as the test statistic and a rejection region, which will be on the top side of the distribution, or large values, which will help us decide whether we want to reject the null. Now, if we change the rejection region, then we will have a different result, and the test will have different properties. Okay, so here is a list of steps that we can use to conduct a hypothesis test. Step 1 and 2 state the null and alternative hypothesis. Step 3, calculate the test statistic. Step 4, find the rejection region. Again, we will discuss this in more detail, how to decide what rejection region to use. But imagine this: there is a set of values which we will consider larger in this specific case, or smaller if we have a less than test. But we will have a region. So if our sample statistic falls in that region, we will reject the null. If not, we will fail to reject the null, and that will be our conclusion. So we will use this general format for conducting any test. So the thing that keeps changing is the parameter. With that, we have a different test statistic. For the test statistic, we have a corresponding sampling distribution, but the overall idea is the same. Okay, now here is how we will decide what rejection region to use. So first, to do that, let's understand that when we are making this decision or conclusion based on the sample, we will not be correct 100% of the time. There will be cases where we will make an error in our conclusion. So when we are doing that, there are 2 types of errors that we could make. So let's say we rejected the null hypothesis. We said the null hypothesis is not true, but actually the null hypothesis was true. So we made an error. This error is called a type 1 error. So whenever you reject the null hypothesis, you could have made a type 1 error, and the probability of making this type 1 error is denoted by alpha. On the other end, let's say you accepted the null hypothesis. Okay, so that means you didn't have enough proof from your sample that the value is larger or smaller. So you say, okay, we accept the null hypothesis. Well, in that case, again, you could have made an error. If the null hypothesis was actually false, then this error is called a type 2 error. The probability of making a type 2 error is denoted by beta. Okay, so here is a 2 by 2 chart to show that. So here is what's happening. If 80 is true and you did not reject 80, then you made the correct decision. But if 80 was actually true and you rejected it, you could have made a type 1 error. On the other end, if 80 was false, but you did not reject it, then you could have made a type 2 error. And if 80 is false, but you rejected 80, you made the correct decision. So probability of type 1 is alpha, probability of type 2 is beta. Our goal is to reduce both type 1 and type 2 errors, but it's so if you but what happens is if you try to improve one, the other one becomes worse. So how we will deal with this is we will deal with type 1 error, and then for type 2 error, if we have a larger sample, then it takes care of that. So we will deal with type 1 error because it's considered the more serious kind of error. Okay, here is why type 1 is considered more serious. You have to, the argument could go in either way, but type 1 is what we will deal with. So if you are looking from the EPA's perspective, type 1 error would be when EPA falsely accuses the company of violating the pollution limits. So this would backfire, it would end up in a costly lawsuit. On the other hand, if somebody is a resident who lives nearby that chemical company, they would probably view as type 2 error being more serious. But we will, like I said, type 2, we will try to improve that by picking a larger sample. In type 1, we will make sure we limit that probability. Okay, now here is what we need to do for conducting the test. This was a general idea. Now to conduct a specific test for a population parameter, and again it could be one or comparing two population parameters, we first need to find a suitable test statistic, and then we also need to specify the rejection region. So there was a method introduced by R.A. Fisher for finding this reasonable test statistic for testing the hypothesis. So let's say, for example, we want to test the hypothesis about a parameter theta of a with a probability function p of y or density function f of y, and then let L represent the likelihood function of the sample. This would need calculus to understand, which the proof is omitted in the book. So we will just talk in general about it and use the final result here. So then let's say if we have the null hypothesis 80 theta equals theta 0, the Fisher likelihood ratio test statistic is given as lambda equals likelihood of assuming theta equals theta 0, which is the null hypothesis, where divide by likelihood of assuming theta equals theta hat, which is the sample statistic. So Fisher reasoned that if theta differs from theta 0, then the likelihood ratio will be so basically this is what we are saying. If theta differs from theta 0, then the value of the likelihood when theta is not different from theta hat will be larger when theta equals theta 0. So the rejection region for the test contains values of theta that are small. Okay. Um, so a simple way of understanding this is that this likelihood ratio would be small if the values are similar, but it will be large if the values are not similar. So let's illustrate this. So we want to test the hypothesis H0 theta equals theta 0 about a parameter theta, and the estimator theta hat will possess a normal sampling distribution with a mean of theta and standard deviation of sigma theta hat. So again, this is coming from the central limit theorem. And again, we are assuming that we have a large enough sample size. So the proof is omitted, but the likelihood ratio would actually reduce down to something we are familiar with. It's z equals theta hat minus theta 0 divided by sigma theta hat. Okay, so this is where we will start. This will be our test statistic. So now we have a normal distribution, which will also help us come up with the rejection region. So there are two types of tests. So to figure out the rejection region, now we first need to understand what type of test we are conducting. So there are two types of tests that we can conduct: one-tail test and two-tail test. When we have a one-tail test, then we are trying to test to see if theta is larger than theta 0. So given value, and we are trying to prove if it's greater than theta 0. So HA will be of the form theta greater than theta 0. The other possibility is we can have a less than test. In that case, HA will be theta is less than theta 0. For both these, we will find the rejection region on Z distribution. So for one-tail test, the rejection region will be located on one side of that Z distribution. For a greater than test, it's on the right-hand side. For a less than test, it's on the left-hand side. We could also conduct a two-tailed test, which means HA will be of the form theta not equal to theta 0. So we will basically detect either the value is theta is larger than theta 0 or value is smaller than theta 0. So it could go in either direction, which means the rejection region will be on both sides of the Z distribution. This will be a two-tailed test. So this is where we end up. So we have a test statistic, which is the Z distribution. We know the Z distribution is normally distributed. So we can divide this distribution into two parts. This is the rejection region, and this is the acceptance region for a greater than test. This is the rejection region for a less than test, and we have a rejection region on both sides for a not equal test. How do we decide this? This is where our alpha comes into play. Remember, alpha is the probability of making a type 1 error. So we decide that value at the beginning of the test. We will say, okay, we are okay making the type 1 error 5% of the time. That means this area, the shaded area, is 5%. Let's say for a less than test, we decided to make our alpha or significance level, that's another name, to be 0.01. Then this area would be 1% of the total area. For a two-sided test, we will divide the area into two parts. Let's say we choose our alpha to be 0.05 or 5%. Then this is 0.025 and this region is 0.025. Okay, so this method is called the classical method of conducting a hypothesis test. And this is the summary for a parameter theta. We first write the null and the alternative hypothesis. We calculate our test statistic Z based on the sample that we have gathered. Then we decide where the rejection region is based on our value of alpha or alpha by 2 for a two-sided test. And we will look at where our test statistic falls, whether it falls in the rejection region. That means we will reject the null hypothesis. If it doesn't, then we will fail to reject the null hypothesis. So this is in general the classical method of conducting a hypothesis test. In the next lecture, we will talk about how to conduct the test using the p-value method. All right, so thanks for watching.